Let's start already by our first speaker, Benjamin Merlin Bumpus, who's going to talk about categories, dynamic programming, CSPs, and beyond. Please take it
Thank you
away
so
already.
much. Thanks so much, and thanks for the invitation. It's been always something I was looking forward to be able to speak at Ithaca. So here we are. I thought before I start, make a little announcement that here at the University of Sao Paulo, we're hiring category theorists. So if anyone's interested, you can get in touch with me. Right, so today I'm going to be talking about categories, some dynamic programs, some CSPs. Really, I figured that, given the slots relatively short, I would give a general overview of some of the things I've been thinking about, some of the things that I find interesting, and focus more on high-level stuff to try to see if, people are interested, if have some conversations and like spur more discussion. So I am interested in category theory and complexity theory, and I decided for this talk that I would make up the name categorical complexity theory, or CCT. And categorical complexity theory, in my opinion, is whatever suitably abstract point of view that we could find to use category theory to organize existing results, which is something that I'm sure everyone here is convinced category theory is particularly adept at doing, but also leveraging new tools from other areas of mathematics and bring them to complexity theory. Developing new algorithms, as I will speak about today, and also posing new questions. And I think that particularly, all of these points are important. The new questions part is the part that I find most interesting, especially since you can see things from a different point of view with a categorical perspective. So maybe I give a little bit of a overview. I think this is a relatively, it's a new field, one that I doesn't necessarily have a name, and I just gave one now. But having said that, there's actually a fair bit of activity going on in this area. For example, there was the 2023 workshop on non-compositionality and complex systems that was organized in Oxford, which wasn't entirely devoted to complexity theory, but had a big component of it. And there's been a lot of work going on, for example, in the whole game comonads direction, CSPs, and some sheaf theoretic methods. I thought I would put some names here of people who have been working on this. I will obviously have missed most people. So if any name is missing here, that's purely out of my own ignorance, or the fact that I didn't have enough time to properly look everybody up. But I just wanted to give some credit to some people that I know that are in the area right now. Some of the co-authors that I'm working with that actually are contributed to a lot of the work that I'm going to speak about today include Althaus, Capucci, Fairbanks, Kocsis, Master, Minichiello, Rosiak, and Turner. And so a lot of my co-authors span from graph theorists to complexity theorists to category theorists to logicians, etc. So there's a big group of people with a lot of different interests. And I think that that's something that makes complexity theory a really interesting area to look at categorically, because it spans many areas and it touches many questions at the heart of mathematics, while also being an area that is in deep need of some formalization and more foundations. So this talk is going to be about thinking about computational problems as functors. There's many approaches to complexity theory using category theory, and I think that and there's also many that I am considering currently, but I think that thinking about computational problems as functors is really natural and something that ought to be considered, and even something that I think Damiano Mazza in a few years back, maybe 10 years ago, in a note mentioned that this should be something that we look at more seriously. And so we're going to talk about that today a little bit. So roughly the idea is you have some category C, and then you have an either co or contravariant functor F that attaches a set of certificates to your problem, to the objects of your category C. And then if you want to think of decision problems, where decision problems are just, when I say that a decision problem is encoded by a sheaf or a pre-sheaf, I mean that when you compose your functor f with the functor decision functor that takes a set to either true or false, depending on whether that set is empty or not, then that encodes a decision problem. There's many examples. Pick your favorite NP-hard problem. You can probably find a way of writing this down as a functor. Three coloring, for example, is a representable functor where you take it's the Hom set in graph onto a complete graph with with three vertices and no loops. You can encode many other problems like vertex cover, dominating set, cycle cover, what have you. Sometimes you have to be intelligent about which category you're using in your domain to make sure that everything's functorial. But the point is this is very expressive and a very natural thing to do. A little bit of background is well, why I'm interested in this dynamic programming. So a lot of this talk is going to be about dynamic programming, how to do it using functorial methods, how to think about obstructions to dynamic programming. But what's really the point? I mean, so as pictured here, there should be a certain degree of incredulity when thinking about complexity theory, because on the one hand, in computational complexity theory, everything is NP-hard, most things that you're actually interested in. And being NP-hard, classical complexity theory just tells you, well, give up. Don't even try to solve it fast. We don't have any reason to believe that you can. However, in practice, people do solve many things quickly. And so the question is, it begs the question, what is the theory that we're missing? The perspective of modern complexity theory or parameterized complexity theory, which is also known as like multivariate complexity theory, is that one contrasts the portending pessimistic views of classical complexity theory by, instead of measuring the running time of your algorithm purely in terms of the input size of your algorithm, you measure the running time in terms also of a relevant vector of secondary parameters, k. And so a fast algorithm in this context is something of the form f of k n to the c, where c is some constant that doesn't depend on k or n. N is a total input size, and f is any old function. So f could be something exponential, but the point is that when k is small, this is a bounded constant you stick in front of your polynomial running time. So in this context, let's talk about dynamic programming. So how do you do dynamic programming? Let's say that you have some input graph G, like this thing that I have here drawn here. You might split this graph up into little pieces. So what I've drawn here is on the bottom is basically what some people would call a path decomposition in graph theory. Path decompositions are special cases of tree decompositions. Tree decompositions have, gotten some recent, or relatively recent category theoretic treatment. I wrote a paper with Zoltan Kocsis, Jade Master, and Emilio Minichiello about structured decompositions, which is basically the thing that I drew here in the bottom. They're generalizations of tree decompositions that make sense in any category. They're diagrams that are viewed as decomposing an object when they build this object as a colimit. Another notable treatment of tree decompositions in the literature using categorical methods is the notion of monoidal width of De La Vore and Zobochinski. Really, what I think that I have been getting at in the years is that I think I'm realizing that growth-and-deque topologies are actually better ways of thinking about how to decompose objects into pieces, that is, relevant decompositions. And I'm not going to speak about this too much. So any mention of growth-and-deque topology or sheaf theory that I make throughout the talk is going to be basically a mention for people who already know about it. So yeah, if it's not something you know about, feel free to just forget that I'm mentioning anything sheaf theoretic. So what's the idea with dynamic programming? You have this graph on the left, you have this graph that you decompose it into this little diagram. You build this graph on the top through the little diagram on the bottom by colimit. And so what do? Suppose you have a pre-sheaf that is attaching local certificates. So think of the solution spaces. So let's imagine we're trying to solve three coloring. Well, what do I do is that I'm going to enumerate all the possible three colorings of every little piece in my decomposition, the thing on the bottom left. So on the right, I have collections of sets of little local three colorings with the associated restriction maps. The coloring functor is contravariant, so I take the inclusion maps on the left and I turn them into restriction maps on the right. And then the key observation is that, well, if I pick colorings, one local solution, elements of these sets, sections, if you want to use that language, such that they pairwise agree, or if you know about the terminology, they form a matching family, then there's a unique lifting as soon as we know that there's pairwise agreement of these local choices of data. So I get a unique lifting into a coloring here on the right of the global graph. So this really motivates the intuition for this paper that I wrote with Althaus, Fairbanks, and Rosiak in 2023, and that currently is undergoing a extension. Emilio Minichiello joined the team, and so we're going to put out a new version with more examples now in 2025. That's the hope. The key part of the paper is that we have this big diagram drawn here that consists of two parts. The first part has something to do with the sheaf condition, and the second part has something to do with the dynamic programming algorithm. On the left, I'm not going to go into this into too much detail. I'm just trying to pass some ideas. On the left, the idea is that you start off with data and decompositions. You can think of this as an input graph in one of these diagrams that builds the graph as a colimit, where if you want to go full sheaf theory pilled, you have a category and a growth and decay topology, and then you take pairs of objects and a covering, and you have two options. You either forget about the covering or forget about the decomposition and just get data at the top, or you remember the decomposition or the covering, and then you do something intelligent with it. This global solution space functor on the top is going to be a genuine sheaf in this case, and the commutativity of this big pentagon on the left is entirely determined by the sheaf condition itself. And this collect arrow in pink is a limit arrow, so it takes a certain category of diagrams, these decompositions, takes limits to build global solution spaces. And the key part of everything I'm telling you about for this dynamic programming algorithm is that basically, if you want to summarize the result of this paper, the key part of this paper is that we give an algorithm to compute the limit, to decide if the limit of a diagram of a special shape exists, or rather is non-empty. So you give me a diagram of a special shape, and this diagram is valued in set, but it could be valued in any topos, but we have a diagram that's valued in set, and you want to know whether the limit of this diagram is the empty set or not. And we give an algorithm for doing this that is FPT, and so it's fast in the sense that I was saying before. So it's something that depends exponentially on the size of the little sets involved, but depends linearly in the number of the sets involved in your little diagram. So this is of independent interest, and we apply it to this case of sheaves, but really you can do more with it than just decide whether a sheaf has a global section or not. So let's talk about that a little bit. So the idea is I have my decomposition of my object and my graph into little pieces, and I enumerate all the local solutions. So I get this, this diagram that looks like this. Again, I'm just giving a concrete, more concrete visualization of what's going on because I didn't want to get into too many details. But as I mentioned before, for those in the know, all of this goes through for growth and decay topology, and I can mention more about this later. But for now, we just have these decompositions. I have a little diagram that builds something as a colimit, and now I'm going to look at what happens when I apply my coloring functor to each piece of this diagram. So on the bottom, I have all of these local sets of all the possible colorings of each piece and restriction maps. And roughly, the idea is that I'm going to color, basically emulating the algorithms that are known for coloring graph, or deciding the colorability of a graph given a tree decomposition. So I'm emulating an algorithm that is well known in the graph theory literature, but we're generalizing it, extending it to a much broader class of objects, really in any category. And roughly the idea, I put the algorithm here mostly if anyone wants to screenshot it or have a look at it, but I'm going to just communicate the idea right now. The idea is if you look at the diagram in the bottom left, pick a solution in there on the top blob of the bottom left diagram. You pick a local coloring, and then you ask, is there a coloring in the next set of solutions over that has that shares a restriction with this coloring I've chosen. If there is no such coloring, I throw away the local coloring I just picked. And if there is, I keep it. So basically, I'm filtering out locally if there are or not colorings. The important thing is that you're changing the sets as you go. So you're doing this by dynamic programming, and so you're never actually computing the entire limit of this diagram of local solutions. Instead, you're doing something more intelligent to determine whether they can exist a global section or not by basically computing by dynamic programming these matching families. Or said in another way, we're computing by dynamic programming all of the local solutions that have extensions to global solutions. So that's the intuition. All right, so for just to give a little bit of an idea, the diagrams in the top left here are drawn like this. You pick a graph G, and then I build from the graph G an attachment diagram, which one way of seeing this is to think of my graph G as a presheaf or a co-presheaf, and then take a integral of this, or Grothendieck construction. And what you get is a category that has an object for each vertex of your graph and an object for each edge. So for example, this diagram on the top left, think of a path with two edges. Each edge gets subdivided into two spans. And then diagrams from such categories into any category D are what I'm speaking about and what I'm calling a decomposition. When I hit these diagrams with a contravariant functor, I get something, or specifically a presheaf, I get something that looks like this diagram on the bottom right. So this what I wrote on the bottom right, which is just now you have a collection of cospans of sets, and you're arranging these in some diagram. And really, the algorithm that I mentioned to you is a way of deciding whether the limit of such a diagram is the empty set or not. And so that's really where the generality of our approach comes in, and that's why it works not just for the topologies or these diagrams, these decompositions I mentioned, but also for Grothendieck pretopologies. But roughly, we have one of our theorems says that I can decide if the limit of such a diagram as drawn on the bottom right is empty or not, and I can do this quickly. So the time depends on the number of edges of my graph G. So the graph G is a graph from which I'm building this special kind of diagram. And it depends on the time of the edges and the number of the edges and the feedback vertex number of my graph G, which is roughly something that measures how far my graph G is from being a tree. If my graph is a tree, then you can forget about that part. And I can do this exponentially in the size of the sets of local solutions. So this is where we get this fast algorithm in the parameterized complexity sense of the word fast. All right. So said more broadly, more generally, the picture looks something like this. I have a Grothendieck pretopology J, for those in the know. And my algorithm lets me compute matching families by dynamic programming quickly. And you end up with a diagram like this that I've drawn on the right. Roughly the idea, I just want to say a few words for those who know about this. You start off with the Grothendieck pretopology. We take a check nerve of this Grothendieck pretopology. And from this, we can compute. You take the one-dimensional part of this check nerve and you kind of unravel it. And what you get is a decomposition in the sense I did before, a bunch of cospans of sets whose limit is f, if and only if f is a sheaf. And well, not if and only if, well, if f is a sheaf, then the limit of this thing is exactly f of that object. If you didn't follow that, that's not so important. The point is, this has practical application. So in the paper with Althaus, Fairbanks, Rosiak, and Minichiello, where we outline all of this, we show that we can capture, using this method, we get dynamic programming algorithms for constraint satisfaction problems, which are a huge class of problems. If you want to learn more of them, I know that Tomasz Jakl is in the participants, so he has a wonderful paper about CSPs, so you might want to chat to him too. I also have, so in this paper, we talk about CSPs, but we actually give something that's a lot more general, because it's not just about CSPs, which are defined on relational structures, but we actually capture a lot of things, in particular, any representable presheaf and sufficiently nice categories where you have one of these, you need to be able to have a Grothendieck pretopology. But any representable pre-sheaf, we can decide quickly if it has at least one global section or not. In a forthcoming paper, which will hopefully be out by the end of the year, I also give a similar result for co-CSPs. So these are for co-representable functors. And this is with William Turner, who's a PhD student in Germany. All right. So this was a very, very fast overview where I've tried to like spare you most of the details and just give you a feeling for what's going on, because I figured sometimes it's nicer to have just an overview and have an idea of like what other people are working on. And I wanted to speak about some of the issues that one might have when trying to push this further. And what are, I just gave you a positive, something in the positive direction. So it only feels fair and balanced to give you something in the negative direction. So as we would say in Italian, dito nella piaga. So, here we are. When does this not work? So I mentioned to you that, well, this works for nice enough functors, basically. You need to have the correspondence between the computing the value of the functor and being able to split this down into the limit of some diagram, as I mentioned. That's really the key part of our algorithm. And so one way of phrasing this, which is not the most general way, but one could ask, well, when do we have pre-sheaves, for instance, that encoded in a computational problem, which are just pre-sheaves, they're not sheaves? One example of such a pre-sheaf is vertex cover. So vertex cover is the NP-hard problem. You're given an input, a graph G, and an integer k. And the question is, you have to decide if there's a vertex subset of your graph, which is small, in the sense that the vertex subset has at most k vertices, and such that this vertex subset touches all of the edges in the graph G. Or another way of saying this, that my graph G, when I remove this vertex subset S, has no edges. A graph with low vertex cover number you can think of basically as being a star, roughly, where the center of the star is the set S of few vertices. So why is this not a sheaf? Well, really it's this integer k, this size bound. If you remove the size bound, you do get a sheaf, but it's an uninteresting computational problem because the answer is always yes for a graph if you remove the integer k. But with the integer k, you get an interesting computational problem, but it's not a sheaf. So for instance, here I enumerate all of the local vertex covers of size at most 2, where I'm picking them with the black vertices. And so I have size at most 2. Then I can pick one of these matching families. I pick them with the red vertices. I pick one of the matching families, and here I have these local solutions that pairwise agree, but if you look at what happens when you glue them together, you get 3 vertices in the glued vertex cover. They will always give you a vertex cover if they match, but they don't. But they might not be small anymore, the produced vertex covers. So one question is, well, is there a nice categorical language for quantifying these failures of being able to glue things together? In computational complexity theory, especially in parameterized complexity, a lot of people think about this and talk about it informally. You want to know about these failures, like in which ways could it go wrong to naively just try to pairwise match things and build your solution recursively. Because once you know about that, you can construct algorithms that take this into account. They're more complicated dynamic programming algorithms, and so it would be nice to have language to talk about this. So in a first step towards reaching a point where we can give a categorical account of these broader class of dynamic programming algorithms, specifically fast dynamic programming algorithms for things like vertex cover, we need to have some general mathematical language that lets us talk about these failures. And so far in complexity theory, there is no such language. People do it ad hoc, case by case. So this got me interested in cohomology. So I'm just going to briefly go over this, assuming people know a little bit about cohomology. If you don't, you roughly think of it like this. I have an object X that I want to decompose into little pieces. I have these little pieces, these UIs, and I can build this complex, or roughly this, I got this simplicial object that I'm describing here, where I have the UIs are the pieces, the UIJs are pairwise intersections or pairwise pullbacks of the pieces, the UIJK are three-way intersections, etc. And from that, you can define this complex here. Now, this is all the standard way of defining the cochain complex for check cohomology. But there is one difference, which I want to highlight here, is that we're not using the usual cochain complex, we're extending it one to the left, which basically by taking into account the maps from the global sections or the global solutions to the local pieces, the restriction maps. And this is very important. Adding this arrow means that everything you know about sheaf cohomology doesn't behave exactly the same. It does for H1 and above, but for H0, it's different. For H0, we now have, it's not just global sections. This is now quantifies exactly how far you are from matching, from having the surjectiveness condition in the sheaf condition. And so this is exactly what we can do. H0 of any pre-sheaf F now computes, and there's one way of thinking about it, computes exactly the obstructions to the dynamic programming algorithm I gave you before. And so when we, in a paper with a student of mine, Ani Beatriz Azevedo, here at USP, together with Capucci, Fairbanks, and Rosiak, which is a forthcoming paper based on a short note I wrote with Capucci, Fairbanks, and Rosiak last year. We spell this out for a variety of computational problems. For example, we show that for vertex cover, H0 is exactly those vertex covers that are small locally. But when you match them up pairwise, you end up with a vertex cover that fails to satisfy the size condition you were trying to aim for. And this captures lots of other emergent patterns. So for example, if F is the cycle cover problem, so it's a functor that attaches to each graph the collection of all vertex subsets that are small and whose removal kills all the cycles in your graph, meaning whose removal gives you a graph that's a forest. Now, if you look at the H0 of this functor, it will be describing exactly the two failure modes of this functor being a sheaf. The first is the size condition, the same as vertex cover, but it also describes exactly all of those emergent cycles. So these are the cycles that you don't see locally in your decomposition or in your cover, but that you do see that emerge when you start trying to piece together local solutions. And so this is nothing necessarily new for those who know about cohomology or accustomed to topology, but the insight is that this is useful and describes something that is absolutely fundamentally relevant to people who are trying to describe dynamic programming algorithms for computational problems. And a big research area that I would like to explore more, and if anybody's interested, we should talk more about this, is finding ways of leveraging this language, exactly, having formal grasp of these obstructions for dynamic programming using cohomology, and trying to combine this with the algorithm I mentioned earlier for sheaves. So I really believe that the algorithm, as I mentioned before, really the key part is being able to compute a limit of a diagram fast, or deciding if this limit is empty or not very quickly. But I don't actually believe that this hinges on our problem being a sheaf. I really think that we can do better for a bigger class of functors. They need not just be sheaves. So this is an interesting area of research. If you're keen, we should definitely talk about this more. All right, so just to give you a summary, what did I do in the talk? I mentioned this categorical complexity theory. It's a new area that I think is really budding. There's a lot of fascinating people who are working in this, proving lots of interesting results. The community is actually getting kind of big, and as I mentioned, I didn't give you a big overview of it because I don't have such an overview. But I think it's about time that we perhaps try to organize ourselves into more of a community. Secondly, I mentioned how we have an algorithm for computing the limit of a diagram that has a special kind of shape, so particularly nice combinatorially flavored diagrams. You can decide whether this diagram has an empty limit or not, if the diagram is in set or actually in any topos, fast. And when I mean fast, I mean in fixed parameter tractable time. So then I mentioned that we can also leverage tools from sheaf cohomology or pre-sheaf check cohomology to quantify failures, obstructions to be able to just apply this algorithm to things that don't behave as nice as sheaves. So in general, we do have some organizing results, not just in my work, also in the work that I've mentioned before, on work on CSPs and the work on game comonads, etc. We are leveraging new tools across all of these new areas, and we're developing new algorithms, such as the one that I mentioned today, and we're posing new questions. New questions are, for example, can we capture more dynamic programming algorithms that are on broader classes of objects? It need not be graphs, need not be the things we typically study in complexity theory. Do we really need sheaves? And really, there's many more algorithms that many more questions that I could go on and on about. But for now, I will stop here. Thank you very much for your attention.
All right, very nice. Thank you for the talk. Yeah, I see some virtual applauses come in. All right, are there any questions for Benjamin? Feel free to unmute yourself. In the meantime, I have a question. So can you share a little bit more of your thoughts of how to go beyond sheaves, so to say?
Yeah, so for instance, one thing that I mentioned at some point in passing. Whoops. I am having a hard time. Oh, here we go. I mentioned here that I have this forthcoming work with William Turner on these co-CSPs. And roughly there, it turns out that it's not really the sheaf condition that's important. It's just that we can represent some computational problem effectively by the limit of some sufficiently nice diagram. And so what we did with this in this paper that we're working on now, that we're finishing writing, is that we have, instead of taking a Grothendieck topology, we take something that's kind of the opposite of that. So instead of having a covering being a bunch of arrows into an object, we have a bunch of arrows out of an object that satisfy some conditions. And it turns out that you can compute with this and still compute a diagram whose limit for sufficiently nice problems. For example, for co-representable functors. So that's one direction. The other direction is that the sheaf condition is very strong. It's telling you that global solutions are given to you by just looking at pairwise intersections, and it doesn't matter the order in which you look at the pairwise intersections. Right? Like all I need to know is that I have a matching family. But in dynamic programming algorithms, the more complicated dynamic programming algorithms, the order in which I compute my local solutions actually does matter, and the order in which I put these together. And so I think that one way for us to go past this is to have a notion of something sheafy that's more directed in that sense. So for instance, you give me a notion of a decomposition, but you have to, or a notion of a covering, where this sheaf-like condition depends on some sort of inductive procedure on the structure you're actually looking at. I have a blog post that I wrote a little while ago, maybe a couple of years ago, where in a day, I showed how to give dynamic programming algorithms using some slightly, it wasn't very nice, but it's a categorical account of two things like vertex cover and Hamilton path. But I've never gone further and actually cleaned this up and turned this into something nice and categorical. And I think that finding the correct abstract point of view for that, I think it would be really worthwhile. So if anybody's interested, I would love to chat about that more.
Thanks. Okay, quickly, there's a question in the chat. So let me get it. Yes. So Thomas is asking, any relationship of the cohomology obstructions and Adam O'Congyle? Sorry, I don't know how to read it. Can you read the chat? Cohomology results on CSP?
So yeah, well, so okay, so Adam's result on the cohomology and CSPs, he's considering, well, so for CSPs, the CSPs are sheaves. And so the result that Adam gives is using H1 for the sheaves. So H0 in the case of sheaves is not really telling you anything too interesting. It's giving you global sections. And H1 is what Adam is using to give an algorithm that is, it doesn't have the speed that we obtain in our dynamic programming algorithm. In fact, I don't believe it's an FPT. But I thought that that was very interesting use of cohomology because it's showing, in my opinion, that there is a lot to be leveraged in cohomology that we don't yet know how to do in the algorithms world. I was looking at our cohomology results for pre-sheaves, where H0 does have a lot of information because it's telling you how things fail to patch up locally. And perhaps there's a way of putting those two things together. I've actually spoken to Adam a little while ago, so if people are interested in this, I think that there's definitely directions for collaboration there, but I don't have anything super concrete to say.
Yes, thank you. Any more questions or comments for Benjamin? Okay, doesn't seem so. So let's thank our speaker again.